So in this problem, the question is as follows. After a yearly checkup, your doctor has bad news and good news. The bad news is that you tested positive for a serious disease and the test is 99% accurate. The probability of testing positive when you do have the disease is 0.99, which is the same as a probability of testing negative when you don't have the disease. So what I'm going to do first thing is I'm just going to find some random variables. So the first random variable over here is D, which signifies that that you do have the disease. And when I use not D, that tells you you do not you do not have the disease. Now when I use the random variable t, that says the the test indicates that you have the disease. And when I use the random variable not t, that implies the test indicates that you do not have the disease. Okay, so these are just some random variables that I'm going to use in my problem. And what we can do first thing is we can at least write 99% in terms of probability and in terms of the data, or in terms of the random variable that has been provided. So when I say it's 99% accurate, what it really indicates is that the probability of the test actually is showing that you have the disease, given that you really do have the disease. That's the accuracy. This accuracy happens to be 0.99, which is the same thing as saying the probability of the test showing that you do not have the disease, given that you really do not have the disease, is also 0.99. That's the accuracy. Okay, so the good news is that this is a rare disease striking only 1 in 10,000 people. Now you also know that the probability of the disease is 1 in 10,000. Okay, so given this entire piece of data here, we are asked to find what is the probability that you actually have the disease. So what is the probability that you actually have the disease? Now keep in mind that this is the information that tells you that the bad news is that you have tested positive for a serious disease, meaning you have gone and you've got the test conducted. So the test having been conducted is already a fact that has already happened. So because that has already happened, what I really want to find in this question is the probability of you actually having the disease, given given that the test has been conducted and the test has indicated that you have the disease. Okay, so test has indicated being positive. What is the probability of this expression here? So what you're going to do first thing is we're going to draw something. We're going to draw a simple Venn diagram here. So let's draw the universal space. So here is my universal space of all possible results of my experiment. So this is omega. And what I'm going to do now is I'm going to draw the set T. So here is my set T. And the set T indicates all those people for which the test has been positive. Okay, so I'm using T to indicate the set here. I'm also going to draw a smaller set over here, and let's call this D. Okay, so this is D over here, which is all these people that actually do have the disease. So everything outside the blue set is not T. Everything outside the yellow set is not D. Okay. Now, what is this entire piece equal to? Now, this entire piece equal to from lecture. We remember that this is equal to the joint probability distribution of D and T over probability of T. I'm just applying the conditional probability distributions equation, which is the joint probability distribution of D and T over probability of T. Now I also know that the probability of D and T, now I'm just going to put this on the side here, the probability of D and T is equal to probability of D given T times probability of T. But this is also equal to probability of T given D times probability of D. Both these things are exactly going to give you the joint probability distribution of D and T. Again, these are things taken right from the lecture. So what I'm going to do is I'm going to rewrite the numerator. Of when I say D and T, I'm going to rewrite this as saying probability of T. I'm just going to apply this piece over here. Take that piece over here, which is T and D times probability of D over probability of T. Okay, now what is probability of the test being positive given that you have the disease? Well, this piece over here is completely from that. We already have the data. The probability of somebody having the disease P of D, well, we already have the data for this as well. This is coming from right here. And the probability of the test, how do I find the probability of the test here? Well, the probability of the test is this entire piece here. Is this entire piece in orange. Here. That's the probability of test showing positive. How do I find the probability of this entire piece in orange here? Well, this entire piece in orange can be thought of as the addition of two pieces. First is the addition. I'm going to use a slightly different color here. So first is the addition of maybe this portion in yellow. Okay, and then you can think of, after having found whatever this piece in yellow is, and again keep in mind the piece in yellow is nothing but the probability. This piece in yellow is nothing but the probability of D and T. Okay, so the probability of D and T, once you have that piece here, you can take that piece and you can add it with the remainder of the piece, and let's call this remainder piece again in green here. So everything in green here. Okay, so keep in mind, look at the coloring of my green here. It's everything that happens to be not the yellow piece, but everything also inside this set T. If I can figure this green piece out, and if I can figure this yellow piece out, and the yellow piece I already know is D and T, I can just add them up to give me the probability of T here. So this piece in green is nothing but the probability of everything that is T and not D. So if this is D, if this entire piece is D here, not D is outside the yellow circle. And whatever is not D and T, which is this green piece, take that portion and add it with the probability of D and T. And when I add these two, when I add this piece, both of these pieces over here, that is going to give me the probability of T. Okay, so what's the probability of D and T? Well, the probability of D and T is nothing but this piece over here, which is again nothing but the multiplication of these two pieces. What is the probability of T and not D? Well, the probability of T and not D is going to be equal to the probability of T given not D times the probability of not D. So what is the probability of a test showing that test being positive given that you do not have the disease? Well, the accuracy of the test is 0.99, so this piece indicates the inaccuracy of the test. How inaccurate the test is? Well, the inaccuracy of the test here is 1 minus 0.99. Okay, and the probability of we not having the disease is 1 minus 1 over 10,000. Multiply the two together, take that value, which is probability of T and not D, add it with the probability of D and T, and that's going to be a denominator, which is nothing but the probability of T. Okay, so you have every single piece of this probability that you can plug in, and you can just put in a calculator to find out the probability of d given t. Now, what I want to do first thing is kind of give you an intuition about this problem here. So I'm just going to redraw this. I'm just going to redraw this Venn diagram again. And my apologies because it's become a little messy here with all these coloring, but I'm just going to redraw it again. And so let's just erase everything inside this. And I'm just going to draw the set T again. I'm just going to draw the set T again. So let's say this is my set T, which is for all those people but a test has indicated positive. So this is T. Okay. So keep in mind again here, this is just T by itself. This is just a probability of T. It's not being conditioned on D or not D. It's just probability of T by itself. Okay. Now I'm going to draw I'm just going to draw a set which is going to be the individuals that really do have the disease. So so let's draw this maybe something like this. Okay, so this is my set D here. Everything in yellow indicates those people that actually do have the disease. Okay, now because this D intersects the set T here, what that tells you is that there are these two components here. The first component over here, let's put this maybe in orange here. Okay, so everything over here in orange. Everything here in orange. This piece over here. This piece over here is defined as a probability of D and T. Okay, so from this entire universal space, there are these people, these folks in orange that actually do have the disease and have been tested, and the test indicates that they have a disease as well. Okay, however, there are some people over here, and let's call these people in green here. This piece in green here. Okay, this piece in green here, and these individuals that also have the disease, but keep in mind, for these individuals the test has indicated negative. Okay, so I have D and not T, and I've got over here which is D and T. Okay, so if I add the orange and the green component, if I add them up, well, if I add these two guys up, what it gives you back is the probability of D. Okay, so if I take this piece in orange and if I take this piece in green here, and if I add them up, that simply gives you probability of people that actually have the disease. Okay, and that should be 1 over 10,000. Okay, now the question is telling you the probability of test given that somebody has the disease is actually 0.99. Okay, what this indicates is that if D has happened, meaning you are now on this entire, your sample space is just this piece here. If this piece has happened, the probability of T happening, meaning probability of a test being positive is 0.99. So if a sample space reduces, then the probability of this orange happening given only on that sample space of yellow is 0.99. So think of this as just the orange piece. The orange piece over here is the probability of 0.99, but keep in mind your sample space has reduced. It has reduced to only be on that region where D has happened. It does not mean the entire sample space. It's just the region where D has happened. Okay, so the probability of a test being positive given D is 0.99, and what you're asked to find is the probability of you having the disease given that the test is positive. So what is the region over here that you're actually looking at? So because T has happened here, that means that you're now your sample space has reduced to only this piece here. So on this white circle, which indicates T, what is the probability? What is the probability of D happening? And the portion of D that resides inside T is just this orange component. So what is the probability of somebody having the disease given that a test has been conducted, which still is a really small probability? If you look at this picture here, you could very well be over here, you could very well be over here, which just indicates that this person over here, this person over here, is a person that doesn't have the disease. It's the person for which the the test has indicated is positive, but the person doesn't have the disease. And and this person over here has the same thing. It's a person for which the test indicates that this person has the disease, but in reality, the person doesn't have the disease. But for somebody that happens to be this orange piece over here, somewhere over here, for this person over here, well, this person is unfortunate because this person over here is a person for which the test also indicates that that the person has a disease, and also in reality the person also has a disease here. Okay, so these are the kind of the intuition behind the conditional probabilities and what it really means when you apply it on this problem set.